Hi, my name is David Garraway. I am a student at the City College of New York, Gross School of Engineering. I'm a part of the Advanced Mechatronics class, and today I'll be talking to you a bit about exoskeleton modeling. So, why are we talking about exoskeleton modeling? Currently, robots are becoming quite popular, especially soft robotics and core robots. These basically can attach to a human and give them assistance when necessary. Now, as these soft robots continue to develop, what's important is that they are high performance actuators. And these high performance actuators, they need to be highly compliant, meaning that they have good backdrivability, they need to have high bandwidth, and they also need to be lightweight. So some of the actuators that I'll be talking to you about today are the series elastic actuator and the quasi-direct drive actuator. Now, let's talk a bit about those key components that I mentioned. The back drivability is important because it provides less resistance to motion. You are able to move in the reverse direction. System complexity is reduced. You also get decreased friction and there's lower inertia. And here we can see the transfer function for back drivability, and we'll see how it's applicable a bit later on. Now to bandwidth. Bandwidth is basically how well the system responds. Now, especially in robotics, they um they respond up to the point of -3 decibels. A higher bandwidth generally provides stiffer motor performance and less error. Also, it improves transient response time. And here we can see the transfer function for bandwidth. Okay, so now we get a good comparison of the two actuators that I mentioned, the two models. The quasi-direct drive actuator compared to the SCA, the QDD doesn't have a spring. It also has a larger torque motor as well as a smaller gear ratio. And we can see how it stacks up against each other. The QDD has high backdrivability, high bandwidth, and low mass. But we'll take a look at the results of it later on. Here we have the parameters that I inputted into Simulink and MATLAB. Here's the bandwidth model that was run. We can see the MATLAB codes here that were used to run the system. We see the PID controller, which can be manipulated. Now manipulating these values gives different results. When I increase the proportional and the integral gains, I saw a decrease in bandwidth, while increasing the derivative gain, I saw an increase in bandwidth for both the QDD and the SEA. And we have the transfer function blocks here. You can see how everything is linked. Now looking at the results for the QDD bandwidth, we can see that when we took the value when it reached -3 decibels, and I was able to get a frequency of 110 Hertz. And when you compare that with the bandwidth that I attained for the SEA, that's quite good. The QDD is more than 12 times that of the SEA bandwidth. Here we have the model for the backdrivability setup. Again, we can see the codes, the MATLAB codes down here, have the different transfer functions. Well, here's a comparison of the backdrivability for the QDD and the SEA. Now we can see that the SEA has a high resistive torque, 12.09 Newton meters when compared to that of the QDD, which only had a resistive torque of about 1.971. And the lower resistive torque is more desirable. That means high backdrivability, as I mentioned earlier. Now a bit on what I've learned throughout this course. This course has been very informative, and I'm glad that I took it. I was able to learn about soft robotics and their various applications in our real world today. I was surprised by how prevalent they're becoming, especially in the medical field. I've never used MATLAB or Simulink before, so this was a good experience. you know, and I am certain that it will help me in my future endeavors moving forward. Thank you for your time.